In this lesson, we'll cover the definition of rational functions and focus a lot on their graphs. To start with, the definition of a rational function is a ratio of polynomials. So let's look at a couple of examples of what that means. When we say a ratio, we're talking about a fraction, and in the numerator, I want a polynomial, and I also want a polynomial in the denominator. So here's like the most simple one that I can think of, 1 over x. So here we're taking a ratio of two polynomials. Obviously, these can be much more complicated. You could have something like g of x is equal to 50x to the fourth plus 7x minus 2 all over maybe something like x plus 4, something like this. And maybe one last one. How about h of x is equal to 17x minus 3 over, we'll say, x squared plus 1. So these are all rational functions. They're fractions, and in the numerator you have a polynomial, and you also have a polynomial in the denominator. Now, what are the domains of these functions? Anytime that you have a 0 in the denominator, the function won't exist. So the domain of a rational function is every real number except those that make the denominator equal 0. Looking at f of x, that's pretty simple. The only thing that you're not allowed to put in this function is 0. So you could state it like this. Here's the domain. X cannot be 0, but it can be everything else. You can use a much more formal notation called set builder notation, where you use a curly bracket, you write x because you're talking about domain, a vertical line, and then you can input all the x's except for 0. So if you look at g of x, the only number you're not allowed to put in place of x is -4, because -4 plus 4 would put a 0 into the denominator. So I'll say x can't be equal to -4, but it can be everything else. Again, more formally, you could say all of the x's such that x is not equal to -4, saying the same thing. And then this one's a little bit different. In the denominator, are there any numbers that can make the denominator 0? And it turns out that, well, there are no numbers that make the denominator 0. If you try to solve the equation x squared plus 1 is equal to 0, you would subtract 1 to the right side of the equation, but then you'd have to take a square root, and you do get an imaginary number, but here this function is defined for real numbers, so there is no number that makes the denominator 0. So our domain is all real numbers, which you could express like this. All right, so 3 quick examples. What I'd like to do next is focus on, well, what do these things look like if you were to graph them? And I think starting with these would not be a good idea, so let's start with the function 1 over x. It's the simplest one to look at, and I think it'll help us understand much more complicated rational functions. So in example 1, let's sketch a graph of the function 1 over x. To start with, what's the domain? I think we decided that it's all x's except for 0. That's the only one you're not allowed to use. So in my table of values, I think I'll choose, maybe to start with, I'll use 1, 2, and 3. This function says take these numbers and put them into the denominator. So for 1, you'd have 1 over 1, but 1 over 1 is just 1. If you plug in 2, you get 1 over 2, that's a half, or 0.5 as a decimal. And if you plug in 3, you get a third, and I think the trend will continue. For 4, 5, and 6, you'd get a fourth, a fifth, and a sixth. So let's try to plot these points as best we can. So at 1, you get 1. It's right there. At 2, you get a half. At 3, you get a third. And at this point, okay, at 4, you get a fourth. At 5, you get a fifth. It looks like these values are getting closer and closer to the x-axis. So at 10, you'd have a tenth. I won't be able to sketch that in very accurately. But as you go in this direction for x, the values are getting closer and closer to the x-axis. They never actually equal the x-axis, but they drop down like this. And I'll just put an arrow to indicate that this trend continues this way forever. All right, well, what about if we tried some negative numbers like -1, -2, -3? What happens there? Same idea as here, but the only difference is it'll be -1, -1/2, and -1/3. So at -1, you get -1. At -2, you get -1/2. And at -3, you get -1/3. So that would be here, that's -1, -1/2, and -1/3. So the graph goes really close to the x-axis over here like this. So I can't really draw it in, but what's happening is these values are getting smaller and smaller and smaller. They're never 0, but they get closer to the axis. And the same thing happens on this side, except the values are negative. So it gets really close to the x-axis, and I can't really draw it much better. The only thing we really haven't figured out is, well, what happens between -1 and +1? I can't use 0, but I could use like -1/2, -1/3. So if I try that, maybe I'll try 1/2. What happens here at 1/2? I'll be a little bit more careful. Let's plug this into the function. F of 1/2 is equal to 1 divided by 1/2. But if you divide by a fraction, you're multiplying by the reciprocal. This is really 1 multiplied by 2 over 1, which is 2. So if you plug in 1/2, the value you get back for y is 2. The trend is, if you look at 1/3, the only difference is you'd have a 3 instead of all these 2's, so the answer is going to be 3. If you plug in 1/4, you'll get 4. So what's happening is these values are getting larger and larger without end, so the graph goes up like this. And I'll draw an arrow to indicate that that trend continues forever. So as you go from 1/2 to 1/3 to 1/4, the y values are going 2, 3, 4, 5, and it doesn't stop. It just keeps growing. This graph is going up towards positive infinity. And if you compare this to, well, what about -1/2, -1/3, and so on? Well, now you'll get -2, -3, -4. So this and this. So here's the graph. It's zoomed out a little bit, but I see what's happening. It starts here at 1 and then gets really close to 0. But as you go in this direction, it goes up to positive infinity. Over here, they're negative, but it still goes to 0. And here it's going down towards negative infinity. I can see that this graph has two asymptotes. It gets really close to the x-axis and really close to the y-axis. So this line here, which is y is equal to 0, that is a horizontal asymptote. Again, an asymptote is any line that your graph gets closer and closer to. But also, x is equal to 0 is a vertical asymptote. So when it comes to graphing rational functions, if you know where the asymptotes are located, it'll really help you sketch what the graph looks like. So that's going to be our goal. It's going to be, if I have a rational function, can I locate any of these asymptotes, and can I use that to help me get a graph of the function? Let's try this idea in the next example. So here in example 2, we have a rational function, and it's actually a transformation of the graph f of x is equal to 1 over x. And that's what's down here. On this x and y axis, I graphed 1 over x. How is this function different than this one in terms of transformations? I see there's two changes. We have this -3 next to the x, so this is changing the x values. This 2 is outside of the function, so this is changing the y values. The two differences are that this graph is going to go right 3, and then it's going to go up 2. So the question is, if you want to get a decent sketch of this equation, can we first identify where the horizontal asymptote is and where the vertical asymptote is? So where is this? And where is this? Okay, if this graph is moving right 3 and then up 2, I can figure out where the horizontal asymptote is located. It's starting at y is equal to 0. If this thing moves right 3 still is equal to y is 0. But if you go up 2, it now is here at y is equal to 2. So that's our horizontal asymptote. Y is equal to 2. And the reason is it starts at y is equal to 0. This makes no difference if you go right 3 places. But taking this line and going up 2 changes it from y is equal to 0 to y is equal to 2. Now where's the vertical asymptote? Okay, the vertical asymptote on the original function is at x is equal to 0. If I take this thing and go right 3, I'd go 1, 2, 3. It's now located here at x is equal to 3. And if you move this up 2, well, that'll have no effect on it. And that means that the vertical asymptote is at x is equal to 3. What I'm going to do is draw in these asymptotes and then sketch this graph in around it. So I'll start with the horizontal asymptote. That's here. And the vertical asymptote is here. The shape of this graph will be exactly the same as this one. It's just been shifted due to transformations. So it's going to be a very rough sketch, but I'm going to see a graph that looks like this. Okay, so that was using the asymptotes to get a sketch of this function. All right, let's now sketch a graph of f of x is equal to 1 over x squared. How will changing an exponent from just a 1 to a 2 alter the graph? To start with, the domain of this rational function is x can't be equal to 0. The fact that there's a squared here doesn't change the fact that the only number you cannot put in place of x is 0. And for this reason, on your table of values, you can still use 1, 2, 3, negative 1, negative 2, negative 3, a half, a third, and so on, just not 0. So I'll start with, I guess, 1, 2, and 3. And this time when you put in these numbers, these go into the denominator, but they're also squared. 1 over 1 squared is 1. 1 over 2 squared isn't a half, instead it's a fourth. And 1 over 3 squared isn't a third, but it's a ninth. So by squaring, putting a 2 in this exponent, these fractions become smaller and smaller and smaller. So we still get at 1, there's 1, but then you get a quarter, you get a ninth, and this thing is going to 0 much faster. So if I try to sketch this in, it actually looks a lot like 1 over x. It's just that the values are decreasing at a faster rate. So you plug in 4, 5, and 6, these just get closer and closer to 0. Now what happens if you check negative 1, negative 2, and negative 3? This time, because you're squaring the numbers that you put into the denominator, if you square negative 1, it becomes positive 1. Last time with 1 over x, the graph was down here, but since we're squaring, these are all going to be positive numbers. 1 over negative 1 squared is 1. 1 over negative 2 squared is positive 1/4, and 1 over negative 3 squared is positive 1/9. So you get this point, and this point. So here's a pretty big difference. This gets closer and closer to 0, but it's positive on this side instead of negative. All right, what about numbers like, a half, a third, a fourth? Okay, if we check out that, like a half and a third, what's happening between here and here? Well, at a half, let's plug it into the function just to be careful. F of 1/2, that's 1 over 1/2 squared. But if you square a half, you get a fourth. But here we're now dividing by a fourth, and we can multiply by its reciprocal. And so the answer is 4. So at 1/2, you get 4 back for the y value, which is right here. So it will turn out that this thing's going to grow, but it just grows a lot faster than just x to the first power. And if you plug in a third, you get 9. So that's right here. So your graph is increasing to positive infinity, but it's just much faster. And what happens for negative 1/2 and negative 1/3? Well, if you check negative 1/2, if you put a negative here and square it, it goes away, and you'll still get 4 back. So again, this is different. At negative 1/2, you get positive 4. At negative 1/3, you get positive 9. And so the graph looks like this. The takeaway is, if you have an even exponent like this, like a 2, a 4, or a 6, this side of the graph will have this shape, but it won't be negative over here. It'll be positive. Now, in terms of the asymptotes, this graph still has 2. There is a horizontal one. So there's a horizontal asymptote, as well as a vertical asymptote. And these are exactly the same as the ones with 1 over x. Y equals 0 is still the horizontal asymptote, so I'll put that here. And the vertical asymptote is still x is equal to 0, which is right here. So there's a lot of similarities. The domain's the same, the asymptotes are the same, but the big difference is, if this is an even exponent, this side won't have negative y values, but you'll have positive y values. All right, let's use the shape of the graph f of x is equal to 1 over x squared to sketch a graph of this function using transformations. That is, how does this one move from this one? Here, I have a sketch of the graph of 1 over x, and there are 2 differences in this brand new function. I see that we're adding a 4 to the x value, and then we're subtracting a 3 to the y value. Well, this plus 4 will actually move the graph left 4, but the minus 3 is going to move the graph down 3. So what we should do is, if I want to sketch this function, determine where the asymptotes are located, and then sketch in the new graph around it. All right, so on this graph, the horizontal asymptote is y is equal to 0. Left 4 won't change that, but down 3 will. 1, 2, 3. The new horizontal asymptote is at y is equal to negative 3. That's here. So I'll say y equals negative 3 is the horizontal asymptote. And the vertical asymptote, which is x is equal to 0, well, left 4 definitely changes that. It goes 1, 2, 3 here to negative 4. But down 3 doesn't change it. So x is equal to negative 4 is the vertical asymptote. Nothing else about this changes. There's no reflections, there's no stretching. That means the shape of this graph will follow these asymptotes. So I'll sketch that in now. So I know on this side it's going to drop down and then go towards the asymptote. And then this will happen on both sides. So here's a rough sketch of what this will look like. In example 5, we have a graph of a more complicated rational function. I can see from the graph there appears to be a horizontal asymptote and maybe a couple of vertical asymptotes. But the goal here is to determine, as x approaches these values, what happens to the corresponding y values. So let's start with this one here. What happens to the y values of this function as x approaches negative infinity? Now, approaching negative infinity means that you're going in this direction here. So the answer to this question is going to be, well, what happens to the y values, or f of x? I can tell from this graph that y is equal to 0 is a horizontal asymptote. So that means as we move in this direction for x, the y values are getting closer and closer to 0. So that's the answer that goes here. As x goes to negative infinity, the y values appear to be getting closer and closer to 0. Well, what about this one? What about as the x values get closer and closer to positive infinity as we go in this direction? It's the same answer as last time. Since y equals 0 is the horizontal asymptote, f of x, the y values, keep getting closer and closer to 0. For these last 4, here we have x approaches 2, but there's this exponent of negative 1 after that. And over here, there's a 2, but then there's an exponent of this positive after it. What's the difference between these two things? Well, here's 2, and at 2, there's definitely a vertical asymptote. The negative means you can approach 2, but you're approaching it from the left side. And the positive means, well, you're approaching it from the right side. And the graph is doing two different things from those two different sides. Let's start with this one here. As we approach 2 from the left, what are the y values of this function doing? Well, the y values are going up, and it seems like they're not ending. So it appears that the y values are approaching positive infinity. If we compare that to approaching 2 from the right, okay, now the y values are dropping down. This means f of x is approaching negative infinity. Okay, a couple more here. What about as x approaches negative 5 from the left? So this negative means we're talking about the 5, but it's a negative 5. And this means we're approaching it from the left side. So here's negative 5. This is approaching from the left. And here the graph appears to be dropping down to negative infinity. So for this one here, it's also that the y values go to negative infinity. And here for this last one, I see there's not a minus nor a plus in the exponent. And what this means is the same thing happening on both sides at negative 5. Can you say that the function is doing the same thing on both the left and the right? And here the answer is no. On the left, it's definitely going to negative infinity. From the right, it's going to positive infinity. So altogether, since it's not doing the same thing, you can't assign it one or the other. And in this instance, you just say it doesn't exist. So I'll say does not exist. So if there's no positive or negative, we're talking about the same thing from both sides. And if it's not the same thing from both sides, you just say, well, I can't say what it is approaching. For the last couple of examples, what I like to do is come up with a method where if you have an equation, how can you look at this thing and simply determine where the asymptotes are located, the vertical and the horizontal? So for this function, I actually included the graph just so we can confirm our answers. So if you look at the graph of this thing, it appears that there's a vertical asymptote at negative 5 and also at positive 4. What is it about this rational function that determines this? And it turns out that those two numbers make the denominator 0. So if you try to put 0 into the denominator of a function and only into the denominator, that means there's a vertical asymptote at that point. So when I look at this function, I already knew that, okay, well, x is equal to 4 is a problem. That's not in the domain of this function. It makes the denominator 0, and it only makes the denominator 0, therefore it's a vertical asymptote. Likewise, x is equal to negative 5 is a vertical asymptote as well. So these are the vertical asymptotes. They are the numbers that make only the denominator 0. Now what about the horizontal asymptote of this function? What's that equal to? This one's a little bit harder by looking at this graph. Here I state that a horizontal asymptote is equal to the ratio of the coefficients of the highest powered x terms between the numerator and the denominator. And here it's really hard to see what that is because things aren't multiplied out. What I'm going to do is distribute into the numerator and the denominator and see what this function becomes. So here, f of x, if I multiply out the numerator, I get 2x squared minus 6x. That came from multiplying this in. And if I multiply in the 1, I get x minus 3. In the denominator, I get x squared. See, I get plus 5x minus 4x and then minus 20. And if I combine like terms, I get 2x squared minus 5x minus 3 all over x squared plus x minus 20. Okay, written this way, this definition makes a little bit more sense. The highest powered x terms are x squareds, and the coefficients in front of them are a 2 and a 1. So these are the coefficients of the highest powered x terms. The horizontal asymptote is the ratio of these two numbers. So that is, it's y is equal to 2 over 1, or simply 2. So this is the horizontal asymptote. So up here, you probably could have figured that out by saying, well, instead of doing all this work, I know if I multiply this stuff together, I get a 2x squared. So I'm thinking 2. In the denominator, you get a 1x squared, which puts a 1 here. So the ratio would be 2 over 1. And if you draw that in here, if you draw in y is equal to 2, I mean, that seems like a good fit for what this graph is approaching. So the vertical asymptotes are where the denominator is 0, and the horizontal asymptotes are the ratio of the highest powered x terms of the rational function. For this last example, I'd like to determine the horizontal asymptote for these functions provided they exist. We're not going to use a graph, we're just going to use this rule of taking the ratio of the highest powered x terms. Okay, in the first function, it doesn't look so bad. I mean, I see in the top I have an x to the first, the bottom I have an x to the first. The coefficients are a 6 and a 3. So according to this rule, the horizontal asymptote is 6 over 3, or simply 2. And that's it. Now for the function g, we have to be a little bit careful. I see there is an x squared in the denominator, but there is not one in the numerator. We want to compare coefficients for x's of the same power. And there are no x squares in the numerator. But that means you can actually add it in like this. You can say, well, the top is really 0x squared plus x minus 2. And now we're okay because you can say, well, in the top, there are 0x squareds. In the bottom, it isn't written, but there's a 1x squared. So if you look at the ratio, it's 0 to 1. And if we divide these two numbers, you actually just get y is equal to 0. So if the x's are the same, it's simple. You can just divide the two numbers. If one is missing, you have to kind of add it back in. And when you do this, you divide like you normally would, and the number you get is 0. We encounter the same problem here for h of x. The highest powered exponent in the numerator is x to the 5th, but there are none in the denominator. It's just x minus 3. But you can place one into the denominator by putting 0, x to the 5th, plus x minus 3. Now if you look at the ratio, it's 4 over 0. So let's see, that is y is equal to 4 over 0. And if you type that into a calculator, it's going to say error. And what this means is there is no horizontal asymptote. And that is it for this example.